We present Programmable Digital Weaves, 3D printable textile-like materials with sliding connections that mimic the yarn structure of conventional woven fabrics. Elastic lattice-like materials, whose structures can be tuned to achieve desired mechanical properties, hold great promise for many applications in robotics. However, existing methods rely on all fused connections at lattice nodes, which limits the range of mechanical properties that can be achieved. By introducing sliding connections, our method allows for relative motion between crossing strands, thus unlocking a large space of programmable nonlinear and anisotropic material behavior. Our method extends to a wide variety of patterns, ranging from regular arrangements of orthogonal strands similar to conventional woven fabrics, to curved yarns, interlacing closed loops, and active strands for actuation. To create sliding connections in practice, we proceed in 3 steps. We first print one of the crossing strands in the usual way, by following a planar path. The second strand is printed by lifting the print head slightly before crossing the bottom layer strand. Using appropriate settings for velocity, extrusion rate, and nozzle temperature, this motion leads to well-separated strands. Please refer to the paper for details. Finally, we print an arc-shaped channel that is fused to the bottom layer strand, enclosing the crossing strand without connecting to it. This approach lends itself to a fully automated fabrication process that only requires a consumer-level 3D printer based on fused filament fabrication, which is controlled through custom G-code instructions. To allow for virtual prototyping of digital weaves and rapid design exploration, we propose a dedicated computational model for programmable digital weaves, extending existing work for yarn-level cloth simulation to support sliding connections on initially curved yarns. This simulation model allows us to predict the behavior of a given design even before it is built, and our experiments indicate very good agreement with our physical prototypes. We start off by revisiting a regular elastic lattice with all fused connections. As can be seen here, the resulting material shows only little deformation to loads applied along the strands, but buckles out of plane for shearing loads applied diagonally to the strands. When comparing to a structure with all sliding connections, we observe a much softer response to diagonal loads, with strands rotating and sliding to produce large in-plane deformations. As is evident from the sequence, replacing fused with sliding connections has a dramatic impact on the mechanical behavior of the material. Our method generalizes beyond regular lattice structures and can be applied to curved strands and interlacing loops. In this example, we explored the impact of different combinations of fused and sliding connections on a sample made of interlaced squares. When using all fused connections, the corresponding weave exhibits a state of biaxial deformation for uniaxial loading along the horizontal direction of the image plane. To analyze the direction-dependent behavior of the structure, we show a corresponding directional stiffness plot obtained using data-driven homogenization. When substituting all fused connections with channels that allow only horizontal motion, we observe a significant change in the directional stiffness plot with 0 stiffness in the horizontal direction, an effect that is explained by the structure absorbing all of the imposed deformation through internal sliding. However, as we increase the magnitude of the imposed horizontal deformation, all squares eventually reach their sliding limits, and the material exhibits finite stiffness from there on. In addition to fused versus sliding connections, our method also allows for changing the orientation of the channels, thus determining the direction into which sliding can occur. In this example, we changed the orientation of 1 out of 2 channels per corner to reduce resistance to vertical motion. As illustrated on this tiling of interlaced circles, our method is also able to handle digital weaves with curved strands. Finally, our approach also supports integration of active strands that can be used for actuation, which we illustrate here on a planar to parabolic deployment example. Thank you for your attention.